To evaluate our results, we would like to answer the following three research questions. First, is the CEDAR effective in generating test cases with sufficient coverage? Second, does the GP implementation generate efficient test cases? And finally, does the GP implementation generate test cases in reasonable execution time? For the evaluation, we compared our GP test case generator's performance to random search and grammar-based fuzzer Tomato. For the random search fuzzer, it is a naive random fuzzer with strings generated randomly from printable ASCII characters. We run the test cases on .purify and evaluate code coverage metrics, feeding the evaluation results back to the test case generator. To test the effectiveness of CEDAR in generating test cases with sufficient coverage, we generate test cases for the three fuzzers with roughly equivalent length. Since Tomato generates test cases with length somewhere near 450,000 to 550,000 characters, this is chosen as the base length to generate test cases. For Tomato fuzzer, we choose the best possible coverage out of 100 test cases. For our GP implementation, we do not have a strict control over generated test case length, so HTML trees were generated repeatedly until we get a test case with length falling in the range. Parameters of height and width 7, attribute count of 2, and attribute value length of 2 to 5 were used. For random search fuzzer, we chose the minimum length of 450,000 in the given range, but V8 engine triggers out of memory for such dataset. This is predicted to be attributable for the parser attempting to parse a long L-shaped input. We see that the GP test case generator falls short of coverage compared to Tomato fuzzer by about 2.5%. Considering that we've chosen the best out of 100 Tomato generated test cases and are comparing it to the seed test case of our GP generator, we can say that our CEDAR is effective in generating test cases with sufficient coverage. To test the effectiveness of the GP test case generator in terms of both coverage and test case length, and the effectiveness of test case generators in terms of execution time, we generate test cases for the three fuzzers under fitness evaluation count limit of 100. To take into account both coverage and test case length, we choose test cases that optimize our fitness function the best. For random search fuzzer, we generate test cases with random lengths. For Tomato fuzzer, we use the aforementioned 100 test cases. For our GP implementation, we generate test cases with default parameters. We see that under the fitness function penalizing test case length, our GP test case generator generates test cases with best fitness compared to the other two. Tomato fuzzer generates test cases with best coverage, but the test case is several orders of magnitudes larger than the test case generated by our GP generator. Test cases generated by our GP test case generator has comparable length to optimal test case of random search fuzzer while achieving fitness of 72.12%. Considering both coverage and test case length, our GP generator generates efficient test cases. Also, the test case generation takes least time for our GP test case generator due to the structured nature of generated test cases requiring less random sampling than random search fuzzers, as well as less evaluation time compared to Tomato, benefiting from drastically shorter length. Thus, our GP generator generates test cases in reasonable execution time. The results are as follows. Random search fuzzer achieves reasonable execution time and test case length, but has worst code coverage. Tomato fuzzer, on the other hand, achieves best code coverage, but has worst execution time and length. Our GP test case generator has all the three characteristics of reasonable execution time, reasonable length, and reasonable code coverage. The future works that could be studied are as follows. First, we could apply more domain knowledge of scalable vector graphics, MathML, and JavaScript syntax. We could use grammar-based seed amputation as Tomato does while generating test cases. Also, we could apply this to other sanitizer libraries such as HTML Purifier and Lucy XSS. Finally, we could apply this research to browser DOM parsers, which are much more complex than server-side XSS sanitizers and may reveal mutation XSS patterns only visible at client side. This is the end of our final presentation. Thank you for watching.